Our next unit is number theory. So it's sometimes also looked at as the counting principle, and it's not like 1, 2, 3. It's a little bit more complex than that. But have you ever walked into a Starbucks or been standing behind someone in line at Starbucks and they order something that is, you know, like a grande iced decaf cappuccino, half calf, anyway, and they go on and on and on with all these choices. So I don't know if you've ever wondered how many total possibilities there are when you step up to the register in Starbucks. Or I think probably some of you have seen an advertisement for Arby's where they talk about 5 for $5 and then how many choices you have. So that's really what number theory is. That's what we're going to look at. And there's a couple of concepts we'll look at. One is called the counting principle, which is sometimes also called a multiplication principle. And then we're also going to look at two concepts called permutations and combinations. The reality is most of us are not going to be doing those kinds of calculations, but this information actually impacts us on a regular basis. So we're going to look at ways that we can determine how many license plates there are depending on what the configuration of the license plate is. Or I think with the explosion of phones, with people having mobile phones and people, I guess kind of landlines are going away, but looking at, I think each of us has probably experienced some sort of a new area code where we are. The reality is we run out of possibilities. So we're going to look at how we determine that. And they're pretty basic formulas, but I think you'll find it enjoyable to look at some of the examples that we're going to look at and see how some of those concepts are determined. So that the next time you go in to get a new license plate for your car, you may be thinking about, you know, I wonder how many license plates they can actually create using this configuration. Or the next time you go to Starbucks, it'll probably blow your mind how many possibilities there are as you stand up there. So that's what we're going to talk about with number theory, and I will go through how we set those problems up. Depending on what calculator you use, you may actually be calculating them differently, but I'll talk a little bit more about that also in this next segment. So let's look at some examples of number theory. And one of the things that's really important is to think about this general counting principle. Again, it's not just 1, 2, 3. But there's a principle that applies that says if one event happens and then another event happens and then another event happens somehow, that we multiply each of those events together to determine the total possible ways that something can happen. Sometimes this is also referred to as the multiplication principle. So an example that you see in the packet says JR's Ice Cream Parlor lists ice cream or frozen yogurt in 28 flavors each. If you want a dessert from this list, how many choices would you have? So the two events are the fact that we have two types of ice cream. We have ice cream, we have frozen yogurt. So there's our two. And then each of those comes in 28 flavors. So we can multiply that by 28. When we just are choosing between one scoop, there's 56 possibilities. So if we extend that a little bit, let's say we go back to the ice cream place because it was really good the first day. So now we're going to go back the second day. And today we're going to have it on a cone. And let's say they offer 3 types of cones. So they offer, you know, just a regular sugar cone. They offer a waffle cone. And then, you know, the little ones that you get like at McDonald's. I just call them just a regular cone, but they kind of taste like sweet cardboard. Okay. So let's say we've got 3 choices that we can actually have with our 2 flavors, our ice cream or yogurt and our 28 flavors. Now we have 3 types of cones two types of ice cream or yogurt, and 28 flavors. So we actually have 168 different types of cones that we could choose. All right, so that's our overall principle, is that we multiply each of these events together. Now, this is just kind of a general type of thing. If we look at this particular one, this is where we would determine like how many license plates are possible. So in California, I think it goes something like letter, number, 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 letter, letter, letter. That's how they do their license plates. So if I don't really look at any restrictions that we might have, I know that for each letter, I have 26 choices. And for each number, I have 10, because we could use 0 through 9. So we have 10 possibilities. So if I'm looking at the total number of license plates that can be formed with using this configuration, this is what it's going to be. That's a lot. All right? So when we have the general counting principles, that's what we're looking at. We're looking at how many ways each event can happen, and then we multiply those through. Okay? Now, what happens is that with the counting principle, it's kind of like the broad principle of all of these. We then talk about a specific type of counting principle where we are looking at order or specific function as being important. When I had my license plates, it didn't matter whether I had an A here and an A here, or I had a 777. So I was able to use those more than once. We get to a permutation, and that's not going to be the case. I'm not going to be able to use something more than one time. So here's the technical definition of a permutation. It says it's an ordered arrangement of distinguishable objects, not allowing repetitions among the objects. So we're able to distinguish one object from the next. Now, I think the best way to explain this and the notation and all of this is really through an example. So our example here says, the Portland Cycling Club organizes a race in which 5 persons, we're just calling them A, B, C, D, and E, are entered. If there are no ties, how many ways could the race finish? That's a permutation, because each of those bicycles can be distinguished from the other, and we're saying there are no ties. One person is not going to, each place has its own particular spot. That's going to be a permutation, and this is the notation we use for that. A permutation of n objects, and this is how many of those objects we're actually going to consider. So in this particular case, we had 5 cyclists. That's going to be a permutation, and our n is 5. We wanted to know how many ways the whole race could finish. So actually, in this case, we're talking about another 5, because we want to know 1, 2, 3, 4, 5. That's a permutation of 5 bikes. We want to know how many ways all 5 places can happen. If we look at the second example, it says, how many ways could the first 3 positions come in? So the first 3 positions is we just want to consider first, second, and third place. So how many bikes do we still have to choose from? We still have 5. So we have 5, a permutation. This time, we only want to look at 3 of them. So the 2 distinguishing pieces of a permutation will be how many total objects or people or whatever that we are trying to determine. And this piece, the second part, the R, is going to be how many of those we're actually considering within our example. Now, depending on what kind of a calculator you have, you will actually calculate this formula differently. So it's not really, I can't really show you exactly how you will do this. If you're not sure how to do a permutation on your calculator, what you want to do is probably just kind of Google it, because there are many different calculators out there, and they all kind of do it a little bit differently. But for this piece, we're talking about a permutation, which is an ordered arrangement of distinguishable objects. Okay. So the next example is still a permutation, but sometimes when we're looking at permutations, we can't necessarily distinguish one from the other. And the best example of this really is looking at, let's say, letters in a word. So by definition, a permutation where we have like objects is this. In attempting the permutations of the letter, let's say in the word zoo, we must adapt the rule for computing the number of permutations to accommodate the fact that we've got two O's in there, all right? So they're not all distinguishable. And while the formula, I think, looks a little bit daunting, it's not horrible. We're going to be able to work with this pretty easily. The formula says we're going to take the total number of objects. Now remember, this is the same way we determined n here. So total number. We're going to take a factorial, which I'll explain here in a second. And then what we're going to do is we're going to divide out the letters that repeat, or the objects that repeat. So they talk about this. If we look at the formula, it says R1 factorial times R2 factorial times R3 factorial, on and on. So no matter how many are there, that's what we're doing. Factorial is kind of an interesting notation. And what factorial means is if I have something that's written as 5 factorial, what it is the same as is 5 times 4 times 3 times 2 times 1. So it's that number times all the subsequently lower numbers till we get to 1. So if I have 200 factorial, it's 200 times 199 times 198 times 197 all the way to 1. Okay? And so that's really what we're looking at with our n factorial. Now let's look at a couple examples of these. So we'll look at a couple of words. If we look at the word banana, okay? And I want to know how many different ways I can arrange these letters, not to form words. Right now we're just arbitrarily saying to rearrange these. What I notice is I have 1, 2, 3, 4, 5, 6 total numbers. There's my n factorial. So I have 6 factorial up here. When I look at this word, I have 1, 2, 3 A's. So I'm going to divide by 3 factorial. A is there 3 times. And I have 2 n's. N is there 2 times. So I am going to, my formula is going to be, or the way I can figure this out is that I have 6 factorial divided by 3 factorial times 2 factorial. Another example, there's a couple more on in the packet, but let me go to one that might be a little bit more realistic, or maybe not, but you can decide. So it says in a car race, there's 6 Chevys, 4 Fords, and 2 Dodges. In how many ways could the 12 cars finish if we consider only the makes of the cars? So it's not car 1, car 2, car 3, car 4. Is it a Chevy? Is it a Ford? is it a Dodge that's coming across the finish line? So when I'm looking at that example, we had a total of 12 cars. So there's my numerator, 12 factorial. When I looked at my example, I had 6 Chevrolets. So there's my 6 factorial. I had 4 Fords. There's my 4 factorial. And I had 2 Dodges. There's my 2 factorial. So that's how we're going to set these up. And what happens is that if no letters repeated, it would just be whatever our n factorial is. But what we have to do is we have to account for the number of ways those 3 A's, let's say up here, could be arranged in the word, or these 2 N's could be arranged in the word. So order is important, but in this type of permutation, we may have objects that we can't distinguish one from the other. We would use this formula to determine that. Think of this as the same n we're talking about, so the total number of objects or people, and our denominator is just going to be looking at how many of something repeats. That's kind of how I remember this with the R. Okay. So we've looked at just kind of the general counting principle. We've looked at permutations, both of unlike and like objects. And permutations, remember, had a specific order that we looked at. Now when we look at a combination of something, it's really selecting like letters or people or whatever, but we're not going to give them any kind of a particular order or a particular function. And so order is not important with a combination. By definition, it says a combination is arrangement of objects in which order is not important. The nice thing is, notice how this notation looks a whole lot like a permutation. The N and the R are exactly what we've been talking about so far. N is the total number of objects or people that we are considering. R would be how many of those we're going to choose. So wherever you found how to calculate the permutation, the factorial on your calculator, your NCR is going to be right there with it. So in terms of actually calculating it, you will find it in the same area. So let's look at a couple examples. One example says, how many ways can we select 3 letters from the English alphabet? Select them. It didn't say form a word, put into any particular order. It just said select them. So that's a combination. I know I've got 26 letters in the alphabet. I'm choosing 3 of them. So that's going to be a combination of 26, 3. If I look at another example, it says, how many ways can a committee of 2 people be chosen from a group of 4 people? So the total number of people is 4, and I want to choose 2 of them. So I'm going to say that's a combination of 4, 2. All right. Let me give you an example that really, I think, shows the difference between permutation and combination. Let's say in any math class that I'm teaching, I have 25 students. So my total is 25. If I asked a question like this, in how many ways could we select a president, a vice president, and a secretary for a class? All right. Now, you may not think of that as order, but what happens is when I choose those 3 people, they can actually be chosen for any one of those 3 positions. So I am, in a sense, putting them in a particular order. That would be a permutation of 25, 3. If I said to you, in that same class, how many ways could we choose 3 students to represent us on student council? So, not giving them any particular function, they're just, the 3 of them are going to go off and represent us on student council. That's a combination because I'm not giving them any kind of specific task. So that's going to be a combination of 25, and we're going to choose 3 of them. So with a permutation, I have order, I have specific function that they're performing. With a combination, I'm just selecting them. I'm just choosing them. I think that as you do the homework for this section, it's not going to be so much the difficulty of actually solving these. I think what you're going to find is you're going to find that it takes a little while to feel comfortable really distinguishing what's just the general counting principle, what's a permutation, and what's a combination. So to help you distinguish one from the other, I've put a little paragraph at the end of this section, and I want to read this to you, and I want you to be thinking about this as I read it. A problem requiring us to use the fundamental counting principle will allow us to repeat the use of an object, a person, or a number. So classic examples are license plates, phone numbers, choosing ice cream, going to Starbucks. Those are classic just counting principle. A permutation will involve order, specific function, or something that puts a condition on what we are selecting. So examples, competitions where order is important. Selections such as choosing officers of an organization, arranging letters in a word. Those all require us to have some sort of order. A combination just asks us to select it. So putting no conditions on what we select. So selecting committees where we're not giving them a specific function. Choosing letters but not really putting them in any particular order. So what we're not concerned about with a combination is order just doesn't even matter. So as you go through, those are really the questions that you want to ask yourself. What conditions are being placed on each of these problems, and that will help you determine whether it's just simply the counting principle, the permutation, or a combination.